Welcome everyone. Good afternoon if you are in Australia or elsewhere, or good morning for those friends in Iraq. Welcome in this distinguished webinar with distinguished speaker Dr. Riadh AlMahaidi, the founder of the Iraq chapter of ACI. I think today we will have a lot of information, especially of the recent development of what happened recently in the strengthening of concrete structures and also in the repair topics. So let me welcome again Dr. Riadh AlMahaidi and ask him if he introduce himself for brief sentences in the beginning and then start his webinar. Welcome, Dr. Riadh. The panel is yours.
Thanks very much, Dr. Ali, and I'm very thankful to the Iraq chapter of the ACI for organizing this series of webinars, which is, I think, extremely important now, given the fact we are all living now in virtual universe and teaching and sharing information. So it's important that we maintain this connection, and that we do find it to be a very useful way to share our knowledge, share our research and applications in various areas of engineering applications, engineering research. So as Dr. Ali mentioned, my name is Riadh AlMahaidi. I am a professor of structural engineering at Swinburne University of Technology here in Melbourne, Australia. I also hold the position of Vice President of the University for International Engagement. It gives me great pleasure, as I said, I can see many of the faces on the screen here, that very good colleagues and friends. So I welcome you all to this session. So what I will do here is that I will give you a brief of what I want to do in this session, and I'm aware of the time that I'm limited to 1 hour in giving this presentation. So this session is aimed at providing an understanding of the issues involved in some material technology, which is the use of fiber-reinforced polymers in retrofitting of concrete structures. I will also introduce a new material to show you how that works. This is the material of the future as well, in the form of shape memory alloys. I will give you some examples of field applications, and I will give you an overview of the design procedures of strengthening of concrete structures according to ACI 440. This is one of the major committees in the American Concrete Institute that deals with research, codification, and standards in the use of fiber-reinforced polymers in strengthening of concrete structures. Why do we need to do rehabilitation? What's the purpose of rehabilitation? In the United States, according to the American Road and Transportation Builders Association, as of 2016, there are nearly 204 million daily crossings on nearly 60,000 structurally deficient bridges that are in need of repair. There is an equivalent number of such bridges in the UK, in Australia, and Australian government has embarked on a 300 million project to renew and to upgrade the bridges here. And I think the situation in the Middle East, in Iraq in particular, is even, in my view, is even worse than the situation in the West, insofar as the infrastructure is concerned. Just to give you an idea, we are not just talking here about wear and tear. We are talking here about why, the increase in the volume and the mass of traffic on our bridges. So just to give you an example, in Australia prior to 1926, the maximum load that you can expect on a bridge is the 15-ton traction engine. What we see on the road network now is much heavier vehicles like the semi-trailer, 42.5 tons, the B doubles, and the B triples that have the very high axle loads individually, as well as a total mass that far exceeds the design of the older bridges. Traffic volumes, we know that in the Middle East, in Iraq, and everywhere, that the traffic volumes have increased also quite significantly over the years. Just to give you an example, one of the major bridges here in Melbourne, Australia, is the Westgate Bridge. The bridge was built to carry 40,000 vehicles a day. It now carries 160,000 vehicles a day. So the volume of the traffic increased, and the mass of the traffic and the weight of the traffic increased as well. We have done many upgrades of major bridges here in the state of Victoria. So one of them is the Monash Freeway Bridge strengthening in December 2016. And to upgrade these bridges, we use these advanced technologies in the form of fiber reinforced polymers. This bridge here is a curved Suffolk bridge. Most of the applications around the world in the use of fiber reinforced polymers have been done on flat surfaces. In this one, this is the first bridge in Australia that we have strengthened, although the soffit of the beam is curved. And this is the standards, the ACI standards, and all other standards around the world don't give us much guidance on how to deal with curved surfaces. So we did that strengthening of that bridge, and now we have undertaken a comprehensive study on the use of RP on curved surfaces. As you know, so in addition to the traffic volumes and the increases in traffic volumes and mass, concrete degrades with time. So concrete degradation is very important here to consider when we strengthen structures. So the concrete degradation is, you get your reinforcement corrosion, you get chemical damage from chloride or sulfate attack, carbonation of concrete, alkali aggregate reaction leading to concrete cracking and spalling, calcium leaching, and physical damage due to fire, vandalism, explosion, and so on. So there are many causes of damage to concrete that can see during the service life. Just to show you some examples of these degradations, like you have sulfate attack, chloride attack, alkali aggregate reaction, AAR, which is known as the cancer of concrete, and reinforcement corrosion as well. By the way, when I use the pointer, do you see it?
Yes, gone. Yeah, it's okay.
You can see the pointer. Okay, good, because I'm going to use it a lot. Okay. Corrosion, as I said that, and what corrosion causes is the fracture of the concrete surface, because the reinforcement inside this concrete, when it corrodes, it expands in volume. So it starts to push the concrete cover, and you can see the color of corrosion here seeping through these cracks. Many such examples. I mean, there are cases, for example, this one is from Canada, to show how much damage concrete corrosion, the steel corrosion has caused. And you can see the steel reinforcement not only degraded in terms of the size of it due to corrosion, some of the stirrups or some of the ligatures here or some of the ties here have also fractured because of corrosion. So all of these require the attention of structural engineers in strengthening, in repairing and strengthening such structures. FRP systems, let me define to you what FRP systems are. FRP systems are fiber reinforced polymers that have got key advantages. They are lightweight, non-corrosive, very high tensile strength, and they are available in various forms, sheets and strips. The sheets can be wrapped to conform to the surface, any surface that you have, circular or any curved surface. And they are, because of their low density, low weight, they have got a very lower, they result in very low installation costs. You don't need heavy equipment, heavy machinery to handle this material. So they come in the form of fabrics like plumage, like cloth. They come in the form of laminates, as well as they come in the form of rods, like steel reinforcement. They come in the form of rods, and you see the different colors here. The black is carbon fiber, the white is glass fiber. The most common form of fiber that we use in structural engineering applications are carbon fiber. In some applications, we also use glass fiber. Okay. Okay. So you can see here typical Frp strengthening systems. So for example, here, this is column wrapping for confinement of concrete of the columns to increase the strength of the concrete inside this column. This is glass fiber that's being used in the strengthening for shear, and this is carbon fiber that's being used for strengthening in flexures. So the typical Frp stress systems, the previous slide showed you what's known as fabric that can conform to any surface. These ones are strips that they are used for curved surfaces. Sorry, they are used for flat surfaces. So you apply them here, the carbon fiber strip here, you apply it to the surface, and this surface here has to be carefully prepared, cleaned, and roughened. The surface has to be roughened. And when you apply it, and you use epoxy, we use what's known as the two-part epoxy, A and B. And this two-part epoxy is usually supplied by the supplier of the carbon fiber itself. The factors affecting the mechanical properties of Frp materials, it depends on the type of fiber, the fiber volume, fiber orientation, the resin type, manufacturing process, and the quality control. So when we say the carbon fiber, when we say the type of fiber reinforcement, are we using carbon fiber? Are we using glass fiber? Or are we using aramid fiber? So all of these are going to give you different properties. The fiber volume, how much fiber is there in your laminates, so the range of fiber that is that we mix it with the resin to produce the fiber products that we use in strengthening, that usually varies between 50 to 70% volume. This is a very typical stress strain diagram, which gives you a comparison. This is vertical axis in KSI in imperial units, and here it's translated into SI units. And this is the stress strain diagram. Typically, this is the red, this is steel. This is grade 400 steel, 400 MPa steel. It has got a yield point here and around 400 MPa. And this is typically the stress strain diagram. The glass fiber has a strength of about 1400 MPa. So about 3 times the strength, the yield strength of steel. Aramid has got even higher, about 2000 MPa. The highest is the carbon fiber. The carbon fiber has got a strength of nearly 10 times the strength of the steel. You can see it's nearly 4000 MPa compared to 400 MPa. And we also look at the modulus of elasticity. the modulus of elasticity of the carbon is nearly or is slightly higher than the modulus of elasticity of the steel itself. You see that the aramid and the e-glass, their modulus of elasticity is lower than the modulus of elasticity of the steel. That's why in most applications, we prefer to use a strengthening system that has got a modulus of elasticity as close as possible to the modulus of elasticity of the steel. But in some application, the softness of the other materials can be advantageous. So these have got the aramid and the e-glass. They have got some applications in certain structural systems. Then we have got what's known as the high modulus carbon. The high modulus carbon has got a modulus of elasticity that ranges between 2 to 3 times the modulus of elasticity of steel. These are used for very special applications. We seldom use it in concrete structures, but we use it to strengthen steel structures. Some applications use structures it's advantageous to use high modulus carbon. Sorry. Before I move to some more details about FRP and design processes, I would like to show you some field applications. One of the biggest field applications that we have in which we use FRP materials to strengthen a bridge is the Westgate Bridge here in Melbourne, Australia. There's nothing wrong with this bridge. If you look at the cross-section of the bridge, this bridge was designed as a 4-lane bridge in each direction. You see, 4-lane in each direction with shoulders, emergency stoppage, and shoulders at the ends. Because of the increase of the traffic volume, the road authority decided that we need to transform this into a 5-lane bridge in each direction. So the shoulder was made fully operational as a full lane, as you can see here. So it became a 5-lane bridge in each direction, which really means that you have increased the vertical, the gravity loads on the structure, the live loads. In addition, you have increased the flexural, the bending moments, the shear, and the torsion on this bridge. And an assessment of this bridge determined that it requires strengthening. So the bridge was originally, as I said, to take 40,000 vehicles a day. Now it's carrying 160,000 vehicles a day. It's the largest bridge in the world ever repaired with carbon fiber. In total, about 40 kilometers of carbon fiber laminates of various grades and dimensions were used, and about 11,000 square meters of carbon fiber fabric were used in the strengthening of this bridge. And the work was completed in December 2010, about 10 years ago. We have inspected this bridge. We have done extensive inspection to see the existing damage in this bridge, particularly in the form of cracks, because cracks have to be closed, they have to be sealed, particularly if they are active cracks, before we endeavor to strengthen. We carried out an extensive research project that took about 4 months in order to come up with a viable structural retrofitting system in the form of FRP, especially for this bridge. And this was done as the designers were designing the FRP or assessing the bridge, and they wanted us to come up with an FRP system that's going to be very effective. So basically, this bridge was strengthened, as I said, for flexure, for shear, and for torsion. So you can see here these red strips. Actually, the carbon fiber is black, but this is just for the sake of illustration here. These strips that we put on the web of the box girder of the bridge, this is for the shear strength. And these ones at the bottom here, these are for torsion. As you know, in torsional strengthening, you require a full, what we call stirrup. in the form of in steel. Sorry, when we design for torsion, the stirrups have to be closed loop because shear stresses occur at the top flange, bottom flange, as well as on the webs. So these are the strips that you can see here that have been applied to this box girder, these ones. And the technology that we introduced to this is what's known by directional fabrics to increase or to prevent what we call delamination, the delamination of the carbon fiber from the concrete surface. The technology that we developed was responsible for reducing the amount of Rp for this bridge by about 30%, which was quite significant, both in terms of workmen, in terms of the amount of work, time of work, as well as in terms of the cost itself. The cantilevers of that stem from the box girder were there because of the extra load that's coming on this, because of the fifth lane. These cantilevers were also strengthened using carbon fiber strips, as you can see here. Very important here is surface preparation. Surface preparation, if your surface is not clean, if it has got debris on it, or if it has got latins, which is a very weak layer on the surface of the concrete, the technology is not going to work. So what you really need here, is you need to do surface preparation. So what we do here is that we use either water jetting or sandblasting. And this is to give us surface roughness between 0.5 to 1 millimeter. And we do also what's known as pull-off testing. See, the concrete has to have sufficient tensile strength in order for this material with its epoxy to act compositely with the concrete. So the minimum tensile strength that we required for this bridge was 2 MPa. And this is something that we do by doing pull-off testing, which are, I will show some pictures of that test. According to ACI, the minimum tensile strength is 1.5 MPa, but for this particular bridge, we upgraded that. We required a minimum of 2 MPa. And the result of the testing on the bridge gave us between 5 to 6 MPa, so this was no worry whatsoever. We're dealing. So this is during the application process. As you can see, this is, as I said, very light material. What you see, the number of workers here carrying one strip, it's not because it's heavy, but it's just because of the alignment. As you are applying this with the epoxy, you needed a number of people to ensure that the proper application of the Frp system. This is doing work on the cantilevers as well, because this is the top of the cantilever. So putting laminates on the top flange of the cantilever here, of the cantilever beam, to increase its flexural strength. This is where the web of the box girder meets the bottom flange. This is the bottom flange. Of course, the laminates cannot be bent because these are solid laminates. They stop here, and at the bottom here, they also stop here. So what we do is that we use splices. This splice here, we use carbon fiber sheets or carbon fiber fabric to ensure the continuity of force, continuity of stress, transfer between the webs and the flanges. This shows you the cantilever of the bridge, lateral cantilever of the bridge, and this is the Frp strengthening system. This point here, see the stem of this cantilever that is bearing against the bottom of the box girder. This area here, because of the increased load on the cantilever, this is going to cause extra compressive force in this part of the structural system. So this needed to be confined. The concrete here needed to be confined with carbon fiber. And I will talk about confinement later, how confined concrete can exhibit much higher strength than unconfined concrete. As I said, the technology that we developed in the form of what's known as bidirectional fabrics to apply to prevent the debonding, early debonding of the laminates. We studied that extensively and how we applied it to this first application of STAT on the Westgate Bridge. And now it has become a standard in all the bridges that are being strengthened with Frp. So we did an extensive study, as I mentioned, to show that the amount of increase in the load with the introduction of this new technology, we were able to increase the capacity of a single laminate from about 100 kilonewton, 95 kilonewton to about 162 kilonewton, between 100 kilonewton here to about 264 kilonewton, more than double the capacity. That gives you the percentage increase in the capacity, about 162% increase in the capacity. So this is something that we were very happy about, and the Road Authority took that these results of the study and applied this system on this bridge. As you can see here, this technology has been applied also on other bridges in recent years in the state of Victoria. You see these are the shear strengthening vertical strips of laminates and with what's known as bidirectional fabric to increase the pulling capacity of the laminates. This is a close-up of that technology as well. I would like to speak here about a bridge that we strengthened in Baghdad, Al Bridge, and I'm sure most of you know that. Al Bridge was bombed in 2015. A truck was placed on top of the bridge and was and it exploded. It shattered 3 spans of this bridge. Very, very heavy damage, as you can see from this picture. So you're going to ask the question, how is Frp going to work here? Well, it's not going to work. I mean, this is complete damage. What you need is a replacement here. So yes, that's what happened. So you see here the piers needed complete removal and installation of new piers. The girders themselves, these are post-tension girders on the deck. Some of them were heavily damaged and they needed to be removed and replaced, but some of them were partially damaged and they required strengthening. So the completely damaged girders were removed and steel girders were replaced instead of the post-tension concrete. And as you can see, the piers here are new piers, and all the ones were removed and new piers were cast in place to support the deck. Now, the part of the bridge of the girders that were partially damaged, we developed a strengthening system for them to reinstate their flexural strength as well as their shear strength. And this is something that we trained many workers in there. They were trained to apply the Frp, local workers, and it was done in record time. As you can see here, the strengthening of these. So this is shear strengthening, the vertical sheets here. And at the bottom here, there were a lot of strips of Frp laminates to reinstate the flexural capacity of these girders. This is after the completion of the work that was done a number of years ago. There is another application, although this is not concrete, but I would like to say here is that Al-Atabah al-Abbasiyya in Kerberos, they wanted to strengthen the dome of Imam al-Abbas, Ma'ali Shrine, alayhi salam, in Kerberos. So the dome itself is not made of brick, old brick. By the way, this is 700 old dome. So this is a schematic of this dome. It's 450 millimeter thickness and 1200 millimeter at the stem or at the base of the arch or of the dome. In the old days, the way it was strengthened so every time they see that there is a movement, a crack, they will build a steel frame like that to support the dome. But you can see here, this was done in the 70s, 50s, 60s, and 70s. But you can see here what the strengthening that was done in here was actually doing more damage than actually supporting the dome. Because any movement here, and this is a rigid element, any movement here, any settlement, any movement in the dome, this is going to puncture into the body of the dome. So there was a lot of damage due to the internal system that was used at the time. Of course, there was a damage on the domes during the uprising of 1991. So we carried out inspections with the to see what kind of on the kind of technology that was to be used, and eventually what the Al-Atab al-Abbasiyya, what they have done is that they filled all the cracks, they filled all the cavities with epoxy, and then they used carbon fiber composites to strengthen the dome. They removed all the steel skeletons that I showed you that caused damage to the dome, and instead they used FRP. This is the first application in Iraq using FRP system, and the dome is being monitored, and the system so far has proven to be very efficient and very effective. Not only was the dome strengthened, but also the columns of the columns of the structure itself was also strengthened using composites, FRP composite. Now, after I have shown you here some of these applications, I would like to share with you some of the design guidelines as per ACI 440, American Concrete Institute 440. They have come up with design guidelines to be used. By the way, it's not a code, it's design guidelines. So, so the design guidelines of the ACI 440 is one of the most comprehensive in the world in terms of the coverage that it has for various aspects, such as flexure, torsion, shear, confinement, material type, material testing, and so on. I strongly recommend the use of ACI 440 for FRP applications. So the FRP strengthening applications, I would like to review with you here on flexural strengthening, beams, slabs, walls, shear strengthening, beams, columns, walls, axial enhancement, or axial confinement of concrete. Okay. As you know, I'm not going to go into a lot of details here. This is really just to show you that these design guidelines, just to show you that it's a simple extension of our normal reinforced concrete theory. It's just that we have introduced another element to the composite. So for example, reinforced concrete, pre-stressed concrete is composed of steel reinforcement, steel pre-stressing, and concrete. What we are introducing here is an additional element in the form of fiber reinforced polymer. So all the design equations are based on the traditional theory of reinforced and pre-stressed concrete, added to it an additional component, which is fiber reinforced polymer as tension reinforcement. So what we want here is we want the capacity to be greater than the demand. The capacity multiplied by the reduction factor should always be greater than the demand. And this is typically what you will get. So if you have a load deflection diagram like this, so if load deflection of a typical, let's say, beam or slab, it's going to be something like that. So it starts, and then this is the yield point of the internal steel, and it goes flat. It's pretty good, has got very good ductility. This is normal reinforced concrete, unstrengthened. If I need to strengthen it, if there is a need for strengthening, I'm going to introduce Frp, for example, to this beam. For a lightly reinforced Frp, I'm going to get an increase, say, to this level, moderate amount to higher level, heavy amount, much higher level of strengthening. Keep in mind here, once you reach a point like this one or like that one, at this point, what happens is that unless you have used what we call anchored systems, you get delamination of the Frp, and the strength capacity reduces back to the normal reinforced concrete, So it doesn't collapse, but it goes back to the unstrengthened status. If I introduce anchored systems like we used on the Westgate Bridge that I had shown you before, and the ACI 440 now recommends the use of anchored systems, you can increase the ductility of the system to move beyond these points to get sufficient ductility that is as it is required by the standards. If you look at this stress strain diagram for a typical reinforced concrete beam, all I am doing here is adding this carbon fiber or whatever Frp system at the bottom here. So all I'm doing is I'm adding an additional element in tension, in addition to the internal steel, that I need to take into account when I do my calculations. So that's your typical reinforced concrete beam, concrete and compression at the top, the typical stress strain diagram, and at the bottom, the stress in the steel and the stress in the Frp. Okay. So generally speaking, when I apply Frp in strengthening, initially the beam will be it will be under the influence of the dead load, and therefore it is going to have an initial strain. And the Frp, when I apply it, it's going to be passive until the live load comes in. When the live load comes in and then becomes activated, so the increase, the strain in the Frp must not be calculated from zero, but calculated from this point to that point. And on the basis of that, that will give me the force that's required for the equilibrium of this system. So I use the compatibility and equilibrium conditions to come up with the design equations, and this is the compatibility part of the formula, and this is the strength part of the equilibrium part of the formula. So this typically that's what you have. Like that's the most complicated, say, T-beam. Let's say you have got compression steel at the top, you have tension steel at the bottom. Sometimes you have got pre-stressing inside, which is this one. I want to increase the capacity of this by applying Frp at the bottom. And if you look at this, at these strain distribution diagram and the stress distribution diagram, that's your typical for reinforced concrete beams. All I am doing, I'm adding an additional component that requires some more calculations that you can find in ACI 440 or textbooks for that matter. So that's the additional force that comes into the equation. And typically that's what your moment capacity. I mean, everyone is familiar, all designers are familiar with this moment capacity of the cross section. So this is using the rectangular stress block or using the linear strain distribution on the concrete. So you can calculate the moment capacity according to these equations. So concrete in compression in tension, carbon fiber in tension. I am adding the moment capacity contribution of the FRP here, and this is the compression steel at the top. So typically, this is the normal equation that I use for calculating the moment capacity of the section. I just introduce another component to it, which is the carbon fiber. Shear strengthening, there are more details to that, by the way. I'm just giving you the skeleton of the design. There are more details that you need to look into for calculating these strains and the stresses. Shear strengthening, as we typically, that's like if you have got a beam like this one, when we strengthen it for shear, we will use the FRP with the fibers running in the vertical direction, like stirrups, like the way we use stirrups inside. So if you have a typical shear critical beam, unstrengthened, it will fail like that. As you know, shear failure is usually brittle, unlike flexural failure. So that's, you don't see any plateau, you don't see any ductility in the behavior. If I use one ply or one layer of reinforcement for FRP, I might get an increase in the capacity in shear, but again, it's going to fail in shear, and it's also brittle. If I use more of FRP, let's say 2 plies of U-wraps in here, I'm going to change the failure completely. I'm going to avoid shear failure and force the failure to go in flexure. And usually this is the type of failure that we prefer to have in our concrete systems, because flexural failure is ductile. It has got an area under the curve in terms of energy absorption, much better than what you get with shear failure. So I have transformed the failure from shear failure to flexural failure, and that is the desired form of failure. Possible shear failure modes: debonding of the FRP sheet, loss of aggregate interlock, particularly if the cracks have become big, and sometimes you get FRP rupture due to stress concentrations. Typically, that's what it looks like. So when you put vertical strips, and you load this, the FRP is going to resist. It's going to have tension in it. You see this is in black, until the stress level in the FRP becomes of such magnitude that it delaminates from the concrete. I want you to pay attention here to this delamination surface. You never get, very, very seldom do you get the delamination of the strip, or the laminate, or the sheet, or whatever. You don't get this failure at the epoxy line. The epoxy is much stronger than the tensile strength of the tensile strength of the epoxy is much higher than the tensile strength of the concrete. So your weakest point is the concrete. So what you do is that you pull concrete when failure happens like that. Typically, we have done some tests on these beams, full-scale beams, many, many years ago. And so you see these vertical strips are carbon fiber strips, okay? And we tested this and we published the work at the time, and you see that the failure capacity of this, so typically without the strengthening, the capacity of the beam in shear was about 250 to 260 kilonewton. When we used the Cfrp, we were able to go to about 450 kilonewton, much higher capacity than for the unstrengthened beam. So shear, how do we do the calculation for the contribution of the FRP? All you do here is that if you look at this equation, and if you go to ACI 318, that's your ACI code, you will see that this equation here is typically what we use for internal stirrups. The internal stirrups that we use here, they could be vertical or inclined. If they are vertical, you are going to get the alpha here is 90 degrees, and this term here, all of it becomes 1. So you get this equation. So this is, if you use FRP, also the FRP can be used in a vertical configuration or inclined configuration. And that's why you get this equation for the contribution of the FRP. All you do is that you add this component to the VC, which is the shear capacity of the concrete, VUC. VUS is the shear capacity contribution of the internal stirrups, and VUF. PV, of course, if you have got the pre-stressed concrete, this is the vertical component of the pre-stressing force. So typically, the first 3 terms is for your normal reinforced or pre-stressed concrete. Okay, you have added here a new component, which is a contribution of the externally applied FRP. So same as you have got for shear, for shear design of reinforced / pre-stressed concrete. CE is a factor here, is an environmental factor. Remember the environmental factors that you use depending on the degree of exposure here. What kind of exposure do we have on the concrete? And you see is less than 1, 0.95, 0.9, 0.85, depends on the environmental exposure on the system. The final type of strengthening that we use is for strengthening or confining concrete in compression, what we call, and this is according to ACI 440. Typically, this is, I'm going to show you this video that some of the tests we have done about that. This is a concrete cylinder, unreinforced like that, with carbon fiber. And the capacity of this, was more than double the capacity of the concrete itself in comparison after we have applied this confinement of the concrete. Okay. So what are we doing here? So if it's unconfined concrete, okay, compression is going to cause lateral strains, dilation of the concrete in the lateral direction, in the radial direction, and you are going to get all kinds of cracks here. But when you confine the concrete here, and by the way, the fiber direction here in this case is horizontal. So this loop here, this becomes your confining shell. It's like you have the internal steel, either ties or spirals inside the concrete, except that we are applying it outside. So when this concrete tries to expand, that expansion is going to be confined by this ring of FRP, which is going to cause the confinement of the concrete. So this concrete here is going to be under a triaxial state of stress. And the capacity in that case is going to be much higher than the uniaxial state of stress. And typically, that's what you get. If you have the stress vertical axis, strain horizontal axis, and this is the strain diagram in the longitudinal and vertical direction. This is in the transverse direction. Typically, if it's unconfined concrete, you get behavior like that. With confined concrete, you get behavior like that. So you can see the advantage of using FRP as a confining material. There are some sketches here for the FRP jacket and the type of radial stress that it is imparting on the concrete that will eventually cause the concrete strength to get much higher than under uniaxial conditions. We can come up with axial moment interaction diagrams. So that's typically for the unconfined. This is for normal reinforced concrete column. You get an interaction diagram like that. And remember, this is the balance line. Okay. But if you have got with FRP confinement, you get a much higher capacity. But keep in mind that the FRP confinement works only in the zone where the predominant failure mode is the compression failure of concrete. But when you come to this zone here, very little advantage we get for the confining, because in this zone here, the tensile yielding of steel governs the failure of the column. So we can only take advantage of the confinement in the compression failure mode here. Now, I would like to show you a few more slides of some of the research that we are doing now other than Frp, what we call self-pre-stressing shape memory alloys. We have used this technology for strengthening of steel structures quite extensively. But now it's being introduced for strengthening concrete structures. I would like you to look at this video clip. This is a spring that's made of shape memory alloy metal. It's an alloy, okay, SMA alloy. If you stretch it like that, it doesn't go back to its original position. It just takes that shape. Okay. If you put it in warm water, it goes back to its original position. So what you have here, as you said, that's the SMA spring. You stretch it, you put it in warm water, it goes back to its original position. So let's say that it's not a spring, let's say it's a shape memory alloy in the form of a rod, a bar. So you stretch it and then put it inside concrete. Now what you do, you heat this element, you heat this shape memory alloy. How do you heat it? Let's say through electrical wire, electrical current. What does this want to do? It wants to go back to its original position, original length. It remembers its original length, and that's the term shape memory alloy. So what does it do? It puts compression on the concrete. Isn't this pre-stressing? It's as if you are doing pre-stressed concrete without using jacks. So this EMPA in Switzerland started experimenting with this technology here, and these bars here are shape memory alloy bars, and they are being subjected to the electrical current to produce heat in these shape memory bars. And when you subject it to heat, the bars want to go back to their original position. They are going to put pre-stressing compression on the concrete. And that's the concept of pre-stressed concrete. We are doing a lot of work now in Australia on the use of this technology. In fact, we also have got a master's students at the University of Baghdad, civil engineering, who's also doing some work on this shape memory alloy as a pre-stressing material. So these are all new technologies. So you can say you can use this for new structures. So what does it have to do with strengthening? Well, how about if you have got a serviceability issue with a girder in a bridge or in a building? What you can do is that you can apply this pre-stressing externally. You can put it at the bottom here, anchor it from one end, and anchor it from the other end, okay? And apply the pre-stressing, apply the heat. Or what you can do is that you can drill a chase, you can cut a groove inside the concrete and embed this bar inside as a strengthening material to restore the serviceability conditions, acceptable service conditions by reducing deflections and crack widths. So it can be used for new structures, it can be used as a strengthening for new damaged structures. Finally, I would like to share with you a textbook that my colleague, Dr. Robin Kalfat, and I produced in August 2018 on the rehabilitation of concrete structures with fiber reinforced polymers. This textbook has got a lot of design examples based on ACI 440, our own Australian standards, and also British standards, all worked examples according to these different technologies, different design guidelines. And with that, I would like to thank you for listening, and I would like to hand back to the chair, Dr. Ali, to organize. If you have got any questions, I'll be very happy to answer. Thank you very much.
Thank you very much, Dr. Riadh, for this valuable information, especially the final slides with the shape memory alloy, the new way of pre-stressing concrete. Thank you very much. Okay, let me now see what we have. Questions in the chat box and also on the Facebook page, if you let me, Doctor. We have a question here that what about the durability of these materials and the lifetime?
Okay, I mean, this is a very, very valid question. Yeah, this is a very valid question, the issue of durability. When we say durability, particularly with the composites here, carbon fiber, glass fiber composites, what we found that this material is extremely durable, the fiber itself. The problem is with the epoxy that we use to glue this material to the concrete structure. That is the part that requires close attention insofar as durability is concerned. So what do we mean by durability? Durability we mean by wetting and drying, temperature fluctuations, chemical attack, and so on. Temperature variations is a problem. There is something called glass transition temperature of the epoxy. The epoxy, when it hardens, it cures and hardens, it goes into a solid state, like glass. But if you expose it to high temperatures, it starts to melt. So it transforms from the solid state to the fluidy state. And usually these epoxies that we use, they have got a glass transition temperature between 65 degrees to 80 degrees. Now, 65 degrees to 80 degrees is pretty good. I mean, you know, in terms of normal environment, we don't have more than 65 degrees. I mean, you can claim, I mean, in Iraq, the temperature, let's say, goes 50-50 to, and that's you have it now. I mean, but the rest of the world, we don't have that kind of temperatures, right? But we always have to keep a margin of 15 to 20 degrees above the maximum ambient temperature. That's the glass transition temperature. That's the condition that we put. So in Iraq, I would recommend that the glass transition temperature of the epoxy used should be closer to 75 to 80 degrees, because I need that margin. The countries like Australia, southern part of Australia, Melbourne, and all of that, we can maintain 10 to 15 degrees is enough above the, the 80 degrees is going to be well above the maximum temperatures that we get here is about 40 degrees. Okay, so that's as far as temperatures are concerned. The other issue is wetting and drying, humidity. We have done extensive amount of work by way of accelerated testing, by exposing the Frp and the epoxy and the concrete, and while they are loaded until to cyclic humidity and cyclic temperature variations. And we found that the maximum degradation we get in the bond was about range between 15 and 20% under the most severe conditions, which 15 to 20% reduction in the bond strength. That we introduced as part of the CE, if you recall. One of the equations had a CE, environmental factor. So any exposure, heavy exposure, we use reduction factors to ensure that we have got the capacity reduction well covered in there. So that's as far as that is concerned. The other issue is, what if you have fire in the building or on the bridge? Fire on bridges is not that of that importance because of the fact it's an open space. Fire is more significant when you have got closed spaces inside buildings. Well, it's the same thing. What do you do in a steel structure when you have got fire? For a steel structure, you have to protect the steel. You use fire protection. The same thing with FRP. If we want fire rating, we have to use fire protection for the FRP and so on. So, yeah, I hope that I have answered that question.
Yes, thank you, Doctor. Maybe other questions also related to this same, let me say, concern about the temperature. So the other question is about Al Muthanna Bridge project. What were the factors used to account for the very high temperature in Iraq? We know there is no guidelines and codes to allow such temperature.
As I mentioned here, we did use a factor relevant to that CE factor.
Yes.
As I said, because of the high temperatures, which is 50 degrees, 55 degrees, we wanted the glass transition temperature to be at 75 and above on that bridge. And also we used a capacity reduction factor that's relevant to that environmental exposure in Iraq.
So what about the value of this C sub E, Doctor? It was left for the professional engineer. I think it's difficult.
No, it's in the code, Dr. Ali.
Code. So there is a code for that.
Yes, it's in the ACI 440. It has got values. Let me stop sharing. I don't need to share this anymore. Yeah. So that way I can see you can see me. Yeah.
Yes.
So yeah. Just a minute. Yeah. So in that case, just 1 second, please. Let me adjust my camera here. Yeah. Yeah. So what we have here is that we used, as I said, these factors. Sorry, what was the other question about?
This is about, for example, when we want to use such way of strengthening and repair in Iraq, we have the problem of high temperature up to 50 degrees or more. So what can we use in our process here? As you said, that C sub E, we can use C sub E to modify, for example, the strength applied by this material.
Yeah, that's right.
Yeah,
the C sub E is used for environmental temperature variations, not fire. For fire, it's something else. There's another design procedure for fire and fire protection and so on. But let me come back to this one. What you would require is that the glass transition temperature of the epoxy that you use should be of a higher value.
Yes.
And there are epoxies that can go up to 120 degrees, by the way.
Mm-hmm.
Let's keep in mind that we were not the first ones to use FRP in structures. It came from the aerospace industry.
Yes.
The aerospace have been using it as patches for aircraft. When you have got fatigue cracks and so on the aircraft body, they use these patches. Now, if that's the case, what kind of environmental conditions do these flying objects are exposed to? Heavy, much heavier, much more punishing than the environmental conditions that we have on Earth, right? But there they use a much higher, much more sophisticated epoxies to ensure that they get the composite action that is for their FRP. For our applications, we don't need to go that far. As I said, for our applications, there is a range of epoxies that we can use between 65 glass transition temperature up to 120. We don't need to go to 120. We don't have that kind of environmental conditions. Up to 75, 80 is enough for our applications.
Yes. Another question, Dr. here, regarding, I think Dr. Haytham mentioned the slide number 56 in your presentation. His question is about the serviceability limits in flexural elements. How can carbon fibers improve such thing, serviceability limits?
Yeah, so there are serviceability conditions in the, it's the same thing that when you have got internal steel reinforcement, when you calculate deflections, when you calculate crack width, the same procedures apply here when you have got FRP. We don't use FRP to reduce deflection of a member, because once, if you have got a deflected member, okay, and it has got a severe serviceability violation here, if I put FRP, don't forget, if the FRP is very thin, it's not going to add much to the second moment of area, moment of inertia of the second, unless I put a very heavy FRP element, which is really not practical. In that case, if we have the serviceability requirements in a structure, in a bridge, in a beam, we would like to use the more active type of FRP, pre-stressed FRP. Mm-hmm. And we have got many applications like that. You pre-stress the FRP, okay, to introduce to you the desired serviceability properties.
Yes. Let me take a question from the Facebook page, to be fair, from between Zoom and Facebook page. The question is, one of the researcher here, that I had research work on strengthening beams using TRC, textile reinforced concrete. They are carbon fibers without epoxy or polymeric materials. Can I deal with them the same as FRP materials?
Well, the textile material is usually, we use it also here. We embed it in cement-based materials, cement-based adhesives, if you will, which has got a very good properties. But up until now, we have not come up with cement-based adhesives that are comparable in strength to the epoxy, the organic epoxies. So these inorganic cement-based epoxies that are used, that are very good for the textile type of reinforcement. They are very good for heat resistance, by the way, because what you are dealing with is like concrete, right? But the only problem with them, so it's not a problem as much as their strength is not as strong as, but there are certain applications that they will be that they will be more advantageous than they use the organic epoxies. And we have done a lot of research on this issue.
Yes. The other questions regarding the confinement of columns. What about other shapes rather than circular? For example, rectangular or square?
Yeah, rectangle. Okay, as you know, the confinement. Let's go back to reinforced concrete.
Yes.
Let's go back to reinforced concrete. In reinforced concrete, if you have got a circular section with spiral reinforcement, a capacity reduction factor for the column is how much? I forgot what we use in Iraq, because in Australia, the capacity reduction factor goes like, it's about 0.75. If you use ties for rectangular columns, capacity reduction factor is 0.65. Why is that? It's penalizing the ties, because the ties do not have the same confining capability as a circular or a ring type of reinforcement. The same thing with the FRP. In rectangular or square columns, it would work, but not as efficient as it will work for circular columns. And there are design equations. There are in the design equations of ACI 440, It gives you the confinement level for the rectangular as well as for the circular sections. And keep in mind, there is the aspect ratio in the rectangle.
Yes.
If it's more than a certain limit, it will not work, the confinement.
Yes.
It has to be as square as possible with some leeway for a rectangular shape.
Yes, thank you. Maybe this is a question is interesting for me because related to the heritage. What about using, I think you mentioned the dome of the shrine of Abbas alayhi salam, but it's a general question about using the FRP composite with structures built with lime. I think the dome was built with gypsum, I think.
Yeah, well, the thing is that in Kerbala, the Kerbala project, actually the FRP was not sitting on the brick or any of the constituent materials. There was another layer, that cement-based adhesive, that was put internally, complete application of that, and then the FRP was put on that adhesive layer, or on that cement-based layer.
Mm-hmm. Yes.
That's all the applications that have been done are of this kind. Yeah. Even the churches in Italy, there are many applications of heritage in Italy, churches, it's the same thing. They will put a layer of cement-based compound, and on that you put your FRP material.
Mm-hmm. Good.
Yeah.
The other question is related to the shape alloy metals. What about the heat source? Should be still forever, or what will happen after removing the heat source?
No. Once you, and that's a good question. Once you heat it,
yes,
it goes back to its original position, and that's it. You remove the heat.
No need for heat. No more. Yeah.
No more.
No more.
It goes back to its normal environmental conditions.
Yes. Yeah.
No, the heat is just transient. Just put it, goes back to its original position, we remove the heat.
Yeah.
Yeah.
Maybe this is a design question or the detail. I don't know if you can answer it, Doctor. What is the optimum quantity of Cfrp as a % of tension steel in reinforced concrete beam applications? As you know that applying too much Cfrp in the tension side of the beam will cause the migration of the neutral axis down too much and may exceed the overall height of the beam.
No. The amount of FRP that we put, we do not overdo it. We do not over reinforce, if you will. We put an amount of FRP that is going to ensure that I still have the position of the neutral axis to give me the ductility requirement, or that will ensure yielding of the steel at failure, and so on, to get that level of ductility. We cannot say how much in comparison to steel, because these are two different materials. But there are limitations in the ACI 440 as to what is the upper limit of FRP that you can put. Definitely. There is a lower limit, there is an upper limit.
Yes, like raw maximum and raw minimum. The other question is regarding the in the confinement of the concrete column, is there overlapping, and what would be the overlapping between the two ends, the two edges? Yes.
100 to 150 millimeter overlap. 100 to 150 millimeters overlap. Yes, that's more than enough.
I think that's
what we never get. Remember, I showed you that column. Yes. And the failure of it. The failure doesn't occur at the overlap. It just occurs because that's much stronger than the FRPs, because you have got two layers, and what you need is this transfer of stress over that bond length. 100 to 150 millimeter is quite sufficient.
Good. The other question is that are there any local companies in, I don't know if you can answer it, in Iraq that can offer accessible application of CFRP and GFRP that you recommend to contact? I don't know if you are dealing with such companies.
No, look,
Yes.
literally the companies that are well known internationally, Australia, in the Middle East, in Europe, you have got, usually in Australia, we deal with, there are three companies, Sika, BASF, and Fife.
Mm-hmm.
So these are the three main companies. But there are other companies from Japan and so on. But the companies we know in Australia that we deal with are these three companies. For example, Westgate Bridge, the supply of the strengthening of the Frp came from BASF.
Mm-hmm.
Other bridges like that what you use on this M80 project that I've shown, that came from Sika. It all depends on, you know, contractual and cost efficiencies. I know that Sika is in the Middle East. I think Sika is kind of dominant. They have got a bigger share of the market in the Middle East. And I know from my colleagues, some of my colleagues who do research in FRP, they tell me that this is how they source their material for their research from Sika.
Mm-hmm. I think you mentioned that ACI 440 didn't account for the seismic resistance of members. So what about the FRP and epoxy tested under fatigue loading or repeated loading?
Yeah, fatigue and, you know, see, not everything can be covered in a standard. So for example, ACI 440, they have a special committee that's just looking at seismic aspects of the user, because they use it quite extensively. And there is a subsection of ACI 440 that deals design guidelines for seismic, of RP for seismic activity. It's there, they have it. So if we are talking about seismic versus cyclic, if it is cyclic, like, you know, you've got, for example, on a bridge, you've got cyclic loading. You don't have seismic, I mean, you could have seismic, but it's load, unload, load, unload. So it's a fatigue issues in there.
Yes.
Okay. We have done also a lot of research on this, and you know, the loading, unloading on FRP on. And what we found that the effect of loading and unloading was very, very minimal effect on the integrity of the composite material.
Yes.
But seismic something else.
Yeah.
Seismic.
Yes.
Yeah.
Yeah. We may see a new report by ACI regarding this. The other question is the ductility of the material of RP. Exactly when we use the bar instead of sheet as a main reinforcement or using as a near surface mounted.
Yeah, so the ductility is a big issue. Okay, when we use it as a strengthening material, I have got a reinforced concrete, a beam with steel reinforcement. Now I'm adding FRP. The FRP itself is very brittle. You know, you pull it, and then it breaks. There is no yielding, there is no softening. It's just a brittle material. But when I put it inside the structure, or when I put it to a reinforced concrete structure, I'm dealing now with the full system. What I want from the full system is to be ductile. And I mean, the design procedures and the amount of RP that you put ensures that we get sufficient ductility. Does that make sense?
Yes.
So the FRP itself is brittle, but when I introduce it to the concrete section,
yes,
the whole system has to be
the system. Yeah, yeah.
Now, if I use it as internal reinforcement, I don't have steel.
Mm-hmm.
I don't have steel. It's brittle. Now, so you'll say, how can we accept that? Well, we do. I think in Canada, for example, in Canada now they have got design guidelines for the use of glass fiber and carbon fiber bars inside their structures, because in Canada they have got a much more severe problem with the steel because of the ice and the de-icing salts that they put to cause the salt not to cause the snow not to become icy, so that the chlorides in these de-icing salts penetrate into the concrete and they cause corrosion of the reinforcement, and they cause catastrophic failures, parking garages, bridges, and so on. So now they accept the use of glass fiber instead of the steel reinforcement. They use it. But what they do is that they put the margin of failure. So the capacity is much higher than what's required. The margin of failure is pushed very high. But the actual behavior, if you put on it load and up to failure, it's brittle failure. But they accept it.
Yeah, I don't know what is the seismic risk in Canada. Maybe it's low risk, so they didn't care about that.
Not as high as it is in other parts of the U.S. And it's an, you know, yeah, you have to take that into account.
Yeah.
The seismicity.
Yes. Yeah. The other question, I think it's maybe from the practical point of view, when you have the beam column connection, how can you make the strengthening of such connection using the FRP? Because it is maybe a very narrow zone, and it is difficult to put the FRP sheets in such zone.
So it's the connection itself that we want to strengthen?
Yes.
Right? Is that the idea?
Yes.
Yeah. So So there have been some work on that. What in some instances, what they do is that you drill inside the joint. You drill inside the joint, and to create that hole in there, and then you put whatever material that you want to put, carbon fiber, glass fiber, or even steel reinforcement with epoxy to strengthen the joint. Suppose that you have an external surface. So it's a joint like that. I can put on the side of the joint. What they usually put, they use cross reinforcement, the cross FRP.
Yeah.
And most likely they would use glass in that situation. Yeah.
Yes, I think in the last webinar by Yasser, is a PhD candidate in Portland State University, he mentioned such thing by using ropes, drilling inside the joints, and then using flexible ropes, and it's a really amazing way to strengthen the joint. Yes. I don't know if you have another minute, Doctor, because a lot of questions.
Sure. Yeah, I'm happy.
Yeah. The other question is CFRP need many protection layers to act as structural element, which improve all loading durability and fire resistance. I think Dr. Haytham mentioned that above the layers, I think. We did this, something like that? Protect.
Sorry.
Yes.
Can you say it again, Dr. Ali? I missed that because the sound went down.
Yes, CFRP need many protection layers to act as structural element and to improve its performance. I think he means that
layers.
Yeah, protection above the FRP, I think.
Yeah, well, if I am strengthening the soffit, the bottom of a beam,
yes,
or bottom of a slab, I don't need protection. But if I am strengthening a top of a bridge, the top flange of a bridge, then I need protection for that. Because what you are going to have, so on the top of a bridge, what we use what's known as near surface reinforcement. So we cut a groove, we cut a hole in there, we put our bars, and then the asphalt can come on top of that. Okay. Yeah. That's the type of protection that we use. But in most of the applications that we use on the soffit slabs and beams and so on, we don't need protection unless it's fire protection. That's something else.
Yes. For example, the bridge 10 years ago, I think you left the layers as it is in the bottom of the bridge. So no problem of the evaporation of the water and so on.
Nothing.
Corrosion.
No.
Okay.
No, there's no corrosion.
There's no corrosion.
It doesn't corrode. No.
Yeah. The overloading, other than inevitable weathering, is one of the points which forces us to use FRP or strengthening in general, like the example mentioned in Westgate. how come they did not use a proper traffic growth factor to basically eliminate the cause, especially a country like Australia?
So you mean you design it from the beginning like that?
Yes.
To take the load of 20 years down the line.
Yes, yes.
Yeah. Look, this is all depends. I mean, if you have got a certain amount of money to build something, I mean, if I anticipate that in 30 years or 40 years, the volume of traffic is going to be double, would I put my money now to build a structure that will take the traffic of 40 years later and invest so much money? What are the technologies that I'm using now? Would they be sufficient for 40 years down the line after that? So it's not an easy issue. It's not really an easy issue. You can take into account the volume of traffic and how much it is, up to a certain point, And after that, you say, deal with it at the time when this happens. So for example, the volume of traffic, all they did is that, as I said, 4 lanes, they made it 5 lanes. I mean, the 4 lanes will still work, except that the traffic would be slower.
Mm-hmm.
So in 5 lanes, the traffic is going to be faster, right? So it's just, common sense here. Traffic engineers do introduce these things in their calculations and so on. So you can say, ask the question, how come in the US, the traffic system is so heavy? I mean, on the highways. They call it sometimes parking lots, not highways, because the slow traffic. Didn't they take that into account? Of course they did. But could they have used 10 lanes in each direction? Of course they can. But you have to have land, you have to acquire the land, you have to acquire, you have to invest so much into that. So it's not an easy issue. Yeah.
Yes. A lot of greetings from your students and friends. I cannot mention all the names because maybe you see some of them now in the cameras. But it looks like from Dr. Hakem on demand webinar, he asking on a future webinar regarding the Cfrp as roads and as a reinforcement in concrete from you in the future. If you can, Doctor. Okay. Inshallah. Again, back to the seismic load. The question is, what is the increase of FRP in the case of seismic load? Compare that with that of static load. I think you have some research about that of Iraqi students in your lab at Swinburne University.
Yes. We had some students who did some work. Actually, we had some students who have done a lot of work on, if I can see a picture here of Dr. Yaman Al-Kamaki, he did a lot of work. He's now at the University of the Hood.
He did
work on fire. Very nice piece of research. He published many papers on that. And we had other students who used for seismic activity of RP in columns as a confinement reinforcement and their seismic effects. Other students used shape memory alloys on steel. But I couldn't talk about that here because we're talking concrete here.
Yes.
So yes, we're very a lot of our ex-students now, they became experts in these applications.
So now we ask them to give a webinar like you, Doctor. Coming weeks, like Dr. Yaman and others. All of you are welcome to give webinars from your experience. Yeah. The other question is regarding the shape memory alloy. It was used as a flexural reinforcement?
The shape memory alloy is, we have to keep in mind here, yes, so it's used for pre-stressing. It's not as a normal reinforcement, passive reinforcement, it's a pre-stressing. And instead of using pre-stressing bars and bringing jacks and jacking and all of that, but keep in mind here, We are talking here at a low to medium level type of pre-stressing at this stage with shape memory alloys. It's not going to be like your pre-stressing strands and the efficiency of your pre-stressing strands for long span bridges. It is to be used for moderate spans. It's going to be used for sometimes, inside buildings or on bridges. And the applications are still at their early stages. It's not really very well developed at this stage. We do not have design guidelines for it. Okay, but I see it as really material of the future for pre-stressing.
Yes, yeah. Let me take another question is, how can we use the Cfrp with epoxy agent in the strengthening system in Iraq? And we now have the temperature. I think this is the same you mentioned, the 50-degree temperature. But the note here is regarding the CE coefficient. It is not related to high temperature.
No.
You mentioned that, yeah, yes. So I
no,
think
this is for
yes.
This is for cyclic humidity, wetting, drying, exposure to the outside weather, and so on.
Mm-hmm. Mm-hmm.
And even cyclic temperature, not necessarily going to the TG. Let's say you've got 50 degrees. What happens between 2050, 2050, 2050 if you get that kind of cyclic temperature?
Yes.
Mm-hmm. So that becomes part of it. Once you go, so we have got this range of temperatures, the range of temperatures within the environmental conditions, which is really combined temperature and humidity and mechanical load, versus high temperatures, which is the category of high, extreme temperatures, fire, and so on.
Yes. Yeah. Yes. Yeah. I think we finished all the questions. Maybe we have some comments via speaking. If you let us, Doctor. I know your time is limited, but let me ask Dr. Haytham to unmute himself, and then he can ask you directly. Yeah, Dr. Haytham, go on. Please unmute yourself.
Thank you, Dr. Ali. Thank you, Dr. Riadh, my prof, Dr. Riadh.
Good to see you.
Also, I am very glad to see you again. Regarding to your saying that carbon fiber used to aircraft, carbon fiber that does not used alone, it will be used in a matrix. The carbon fiber is a reinforcement element to this matrix.
Correct.
In building, we should not use carbon fiber alone. We must protect it against fire, against weathering, against environment. This is my question.
Yeah. So in our buildings, the carbon fiber that we use, it's the carbon fiber as a material, as a dry material. It is embedded into a matrix, and the matrix is the resin.
Yeah.
And when we apply it with the epoxy, okay, as a final product, here comes the question of the protection. What do we need the protection for? If we are talking about fire, definitely we are going to protect it to ensure that we get proper fire resistance, like we protect steel structures. Same way.
Yes.
Like we protect steel structures.
The same way.
The same way. But if I am not required, for example, in bridges, because it's an open space, the fire, let's say that you have got fire on the ground, it's not going to cause, because it's really the combustion and the increase in temperature, it depends on how close the environment is. If you have an open environment, it's not going to be that serious.
Yeah.
And that's, for example, one time someone said, oh, on one of the bridges, a fuel tanker, like it was impacted by another vehicle and it exploded. Well, of course. But do we take into account all of these conditions, all of these extraordinary conditions? We can, but that's going to make the
I see you make in Australia the same protection layers. Yeah. The final picture to the bridge, all carbon fiber are protected. When the worker make the layers of carbon fiber, it was black. Later, they cover the carbon fiber by protection layers.
No, this is if you have seen the picture, this is just paint. Paint
Only
to
paint.
make the carbon fiber to be compatible with the concrete. And if you look at the color of the paint, it's similar to the color of the gray, similar to the color of the concrete.
In Iraq, I use now protection layer against fire. They are spray.
Spray. Very good.
Like spray, I protect the carbon fiber against the flames and other extreme environments.
Very good. Very good. Yes.
At the same time, regarding to the serviceability, as you say, serviceability cannot be improved by carbon fiber because it's a thin layer. It will not improve the moment of inertia of the section. So we need another elements like a steel element or other concrete element attached to the element that we need to improve the serviceability to it. Later in Babylon University, we have a slab designed with a small thickness. It makes excessive deflection. I improved this slab by putting steel section like channels attached to the ceiling after unloading the structure and reinforce this element by carbon fiber.
Okay.
So it will be act like a composite structure. Composite concrete, carbon fiber, and steel.
Yep. Very good. Very good. And I think in the direction of serviceability, in addition to what you said, Dr. Haytham, this issue of the shape memory alloys, this is promising, very promising. Because what you can do is that you can insert a cut. You can make a groove inside that concrete slab or concrete beam. It's like a new surface mounted reinforcement. You put your shape memory alloy bar, heat it up between the two ends using electrical, and it will pop up like pre-stressing, like external pre-stressing. So these are new materials to consider in research. I strongly recommend that you take this on board. Yeah.
It's the new future for structure.
Absolutely.
Shape memory alloy.
Yes.
Thank you.
Absolutely.
Thank you, Dr. Ali. Sorry about it.
Yes, thank you, Dr. Haytham. I am also apologizing from all to not let them at the beginning to speak or raise hands because as you see, we have a lot of questions. But the fortunate thing is that we finished the question so we can hear from you directly. And I promise you there will be a lot of webinars coming. So let me at the end thank Dr. Riadh for his time and for the valuable information. And say to all of you, stay home and keep safe and healthy always in this pandemic situation. So I hope to you a good time and you enjoyed this webinar. And thank you again to Dr. Riadh. Thank you.
Thank you so much for everyone, for you, Dr. Ali, for everyone. I can see many of my, some of them, the cameras are not on, many of my colleagues, some of my ex-students. And I thank you all for joining us in this webinar and hope to catch up physically with you in the future. In Baghdad or Iraq, anywhere in Iraq will have, inshallah. Or when you are here in this part of the world in Australia, we'll be very happy to have you with us.
Yes.
So again, thank you very much. As Dr. Ali said, stay safe. It's not troubling. It's a troubling times that we are in now. Not just you here in Melbourne, we have got some problems. So stay well and stay safe.
Stay home. Yes, this is the. Thank you. Bye for all. Thank you. Bye.
Bye. Thank you very much. Thank you.